The limit of a function is going to be the subject of this lecture, and it's going to be absolutely fundamental to learning calculus. I shall start by taking some rather simple examples and then work my way towards more difficult ones. Let's begin by asking what it means to say that x approaches, let's say, the number 2. That means that x is going to get very, very close to 2. So it could be 1.99 or 1.999, add another 9, another 9, another 9, and you could keep adding 9s over here so that this number x is going to get very, very, very close to 2. Or you could start with, let's say, 2.01, or you could have, instead of this, 2.00001, or you could have 2.00001, and etc. You could keep going, add many, many more zeros with a 1 at the end. These two will approach 2, but it will not be ever exactly equal to 2. Well, let's suppose you had a function f of x, and let's take that to be x squared for now. In that case, as x goes to 2, or x gets closer and closer to 2, or we could say x approaches 2, f of x will approach 4. More generally, if we have, let's say, some number a, and x approaches a, then f of x will approach a limit which we shall call L. So as x gets closer and closer to a, f of x gets closer and closer to L. Sometimes we write this as L is equal to the limit as x approaches a of f of x. Or sometimes we just abbreviate this and in short write lim instead of limit f of x. All this is very simple, but what happens when, let's say, x goes to 0 for something like 1 over x? Now, if you were to write down 1 over 0, then this thing over here is meaningless. It is not defined, undefined. On the other hand, the limit of x goes to 0 of 1 over x is surely some very, very large thing. And we call this infinity. But be very careful, this thing which is called infinity is not a number. So you have to be very careful whenever there is a division by x. That doesn't mean that you can never divide by x. Let's take x over x. Now, as x gets smaller and smaller, in other words, if one takes the limit as x goes to 0, the denominator is going to 0, but so is the numerator. And of course, if you were to cancel out the x's, just divide them, you would get the limit of x tends to 0 of 1, and the number 1 is fixed. Nothing changes over there, and so that's 1. Well, suppose I had limit of x tends to 0 of x squared over x. In that case, that's trivial because that's just the limit as x goes to 0 of x, and that's 0. On the other hand, if I had the limit of, let's say, x divided by x squared, well then that's the limit of 1 over x, and that, as we discussed above, is infinity. Again, I stress that infinity is not a number. Here is a picture that will make the concept even clearer. So, here is the x-axis. There's a point that moves towards A from this direction, and there's going to be another point x that will move towards A in this direction, and on this axis I have plotted f of x. This we are going to call the limit of the function L. Now let me show you how the function approaches L. So as you approach from the left or you approach from the right, you get to the value L. L is the limit of the function f of x as x tends to A from either side. So here it comes and reaches the point x equals A and with height L. It certainly can happen that a function has different limits depending on whether you come in from the left or you come in from the right. Here you can see that as x approaches A from this side, then it will arrive at this limit, which we shall call L minus. L minus is the limit of the function f of x as x approaches from the left. In other words, approaches from slightly smaller values than A. Over here, we shall call this limit L plus. And what that means is that we're coming in from the right like this, and L plus is the limit of the function f of x as x comes in from slightly larger values than A. Look at this particular function, which is defined differently for different values of x. When x is to the right, f of x is 1. When x is 0, f of x is 0, which means that we have this one single point over here. And when x is negative or to the left, f of x is minus 1. So let's draw this function. You can see that this function, as you come in from the left, is approaching minus 1, but as you approach it from the right, you get to plus 1. Again. And so the limit as we come in from the right, in other words, L plus is plus 1. The limit as we come in from the left is L minus equals minus 1. Now the very important point is that it doesn't matter how you define the function exactly at x equal to 0. Instead of f of x equal to 0, I could have written over here, let's say 5 or 1.5 or 2.3 or whatever. It would have made no difference whatsoever to the limiting values that we got from the right or from the left. And so it's so important a point that I must write it down. The value of the function exactly at the point A is not relevant, doesn't matter to calculating L. I'm now going to work out some very simple examples, and there's almost nothing simpler than this. I'm looking at x squared minus 1 over x plus 1 in the limit that x gets closer and closer to 1. Well, if x gets closer and closer to 1, then x squared is going to get very, very close to 1, and I'm going to have 1 minus 1 over 1 plus 1, which is 0. So 0 is the limit of this function x squared minus 1 over x plus 1. Now let me take something that's not quite so trivial. Here, if I was to put delta equal to 0, then look at what I'd get. Square root of x minus square root of x divided by 0. And that's 0 over 0, and 0 over 0, as you know, doesn't mean anything. So this was the wrong way of doing this problem, of finding this limit. Instead, one must imagine delta to be small but not 0, in which case we shall need a little trick, and this will be very useful. So let me write the same expression, but multiply by 1, written in this rather peculiar form. I'm going to write x plus 2 delta plus square root of x divided by square root of x by the same thing. And the reason I did that is because if I look at this, this is like a minus b into a plus b, and you know that's a squared minus b squared. In other words, over here it's x plus 2 delta minus x, and at the bottom I have delta into square root of the same thing, x plus 2 delta plus square root of x. Now at the top the x's cancel out, leaving just 2 delta here. Look at the bottom. Here, provided x is not 0, I can take delta to be so much smaller than x that, well, I can forget about this. I can't forget about this. So this is then equal to 2 delta. Well, we've cancelled out the deltas, so let's not worry about that. This is 2 divided by x plus something we're going to neglect, plus square root of x. So we have 2 times square root of x, and so the final answer is 1 over square root of x. That is the limit of this function here. So the answer is 1 over square root of x. And let's take another example. Here again, if I was to take delta equal to 0, I'd then have 1 minus square root of 1 over 0, and that's again 0 over 0, and that's again nonsense. So let's use our earlier trick. Write the function exactly the way it is, multiply by 1, but 1 written as this way, 1 plus, and you're now used to the fact that this is a minus b into a plus b, and this is 1 minus delta squared over 2 delta squared, and now here I have 1 plus this thing, but delta is very, very small, so I can neglect it in comparison with 1, and therefore over here I have 2. This leaves me with delta squared over 4 delta squared. And so the answer is 1 by 4. I've cancelled this out with this. Let's now try to calculate the limit of sine of x divided by x as x becomes very, very small. Well, here's a quick reminder of what sine of x means. So suppose you have a right-angled triangle. Here is the angle x, which increases like this. If we call this the side P, the side Q, then this side is P squared plus Q squared. And as you certainly recall, sine of x is Q divided by the length of the hypotenuse, which is P squared plus Q squared. We're going to be interested when x is very, very small, which means q is very, very small. And so we have a situation now where if this length is p, then this length over here is almost p2, because p squared plus q squared is very close to p itself. And so the question is, what would this length over here be in the situation where these two sides are almost the same? And the answer is that if this is the angle x, then this side over here is x times p. In other words, q is very close to x times p. And just as a quick reminder, if you have a circle like this, and here is an angle x between these two radial lines, if this is p, then this over here is xp. So that's what we are using here. Now immediately what we've seen is that sine of x, as x becomes small, is going to be pretty close to xp, this height, divided by p squared plus q squared, which is of course p itself. And so sine of x is going to be very, very close to x itself. In other words, what we've discovered is that the limit as x tends to 0 of sine of x divided by x is 1. And that's an important result which you ought to remember. Of course, there'll be other ways of deriving this, but we'll do those after we've studied things like Taylor's theorem and so forth. Let's now try to calculate the limit of this function as x tends to 0. So I have 1 minus cosine of x divided by x squared. Of course, we could proceed exactly as we did before. We could draw a triangle with this being the angle x, p, q, square root of p squared plus q squared, and so forth. But let me simply make the comment first that if I take cosine of 0, which means that when x is exactly 0, then q is exactly 0, in which case I have cosine of 0 is square root of p squared divided by p, which is 1. And so I would have, as if I was to put above over here, 1 minus 1 divided by 0, well, I'd get 0 by 0, and we know that that's no good. We've got to take x to be small but not exactly equal to 0. I'm going to take a shortcut, and I'm going to write 1 minus cosine x divided by x squared as this multiplied by 1, but I'm going to write 1 as 1 plus cosine of x divided by 1 plus cosine of x. No harm in multiplying by 1, as you will surely agree with me. And now I use the formula that we've used so often, a minus b into a plus b, and I get 1 minus cos squared x divided by x squared. And now here I have 1 plus cosine of x. However, if you remember, cos squared x plus sine squared x is 1, and 1 minus cos squared x is just sine squared x. So I have the above exactly equal to this. However, now I'm going to use the fact that as x becomes very, very small, sine of x becomes very, very close to x. And so as x tends to 0, this is going to get closer and closer to x squared divided by x squared into 1 plus cosine of something that's very, very close to 0. So that's 2. And so the result is 1 over 2. We often need the limits of functions as x approaches some very large number. We call that infinity. But what is infinity? It's most certainly not a number. You can't treat it as such. Well, let's see what happens if you do treat it as a number. Let's say that I add 7 to infinity. Well, that's also a very, very large number, and then I should get back infinity. Okay? Since infinity has been assumed to be a number, I can just cancel this out on both sides, and I should get 7 is equal to 0. And of course, that's complete nonsense. Usually taking the limit for large values of x, or x goes to infinity, is not a problem. So if I have 1 over x over here, as x becomes larger and larger, the limit becomes 0. In other words, 1 over x becomes as close as you want to the number 0. Here, the limit is a problem because as x becomes larger and larger, x squared becomes even larger and larger. And there is no limit to this. We actually say that the limit does not exist. And so writing the limit of x squared, x goes to infinity equals infinity, is just a symbolic way of saying that the limit does not exist. What about here? Here we have sine of x, and x is becoming larger and larger. X can become as large as it wants or as small as it wants, but sine of x is always going to go up and down, and it will keep doing this no matter how large x becomes. And so this has no limit. In other words, the limit as x goes to infinity of sine of x does not exist. I'm going to take more examples of oscillating functions. So let's look at this. Sine of 1 over x as x goes to 0. As x goes to 0, 1 over x goes to infinity. And so this is something that's going to be very, very rapidly oscillating as x approaches 0. We've plotted sine 1 over x before, but let's look at it again. So as I come in from the left and go towards the right, sine of x becomes minus 1 and then increases, becomes plus 1, and then goes back to minus 1, and then between plus and minus 1 it will oscillate very furiously before it finally goes to 0 at x equals to infinity. In other words, when x becomes very, very large, we're going to have sine of 0, which is 0. And so let's look at this once again. We come in from the right towards the left, and again these oscillations, and then the function goes to 0 to the left. What that's saying is that in this region over here, near x equal to 0, there is no limit. This function does not have a limit. Well, let's look at this one. Here I have sine 1 over x, but it is multiplied by x. And so you would expect that this will have a different behavior. Let's have a look to see what it looks like. So you can see that again it's a very rapidly oscillation near x equals 0, but that its magnitude keeps going down as we approach x equal to 0, and the peaks are all between these two lines over here, between the red and the blue lines. Therefore, it should be very clear that the limit over here at this point at x equal to 0 is indeed 0. A very similar example is that of f of x equals the magnitude of x to the power half times
sine of 1 over x. And let's plot this as we did before. So you see that it's a very rapidly oscillating function. And the only difference is that the envelope is not the straight line that you saw before. It's the magnitude of x to the power half. But let's look over here. Here we have sine of 1 over x always being of magnitude less than 1, and here x to the power half, which becomes smaller and smaller as we go over here. So the conclusion is that the limit as x goes to 0 of f of x is 0. You can see that the function is approaching 0 as x becomes smaller and smaller.
By now we worked out several examples of limits, and we have some good understanding of what a limit means, but it's not precise enough. What we need is the formal definition of the limit of a function. So let's understand the definition written over here. The function f of x approaches the limit L near the point x equals a. If you can make f of x as close to L as you want by choosing x close enough to a. Let me put a picture before you. So here is an interval that contains values of x, and the value x equals a is in this interval as well. This interval is going to be a small interval. Every point in this interval gets mapped by the function f into some point. So this gets mapped here, this gets mapped here, and this gets mapped here. So if we join up all these points, that's an interval over here too. And this is the point, the limit. Now, the statement that the limit exists is to be read as the following. If this interval, that is to say this interval, is made smaller and smaller, then corresponding to that, if we can find an interval down below, then the limit exists. To repeat, let's take any small interval, and this interval can be very, very, very small. So let me take this interval over here, and it's got various values of f that are centered around the limit L. This is the limit provided that this interval here has been mapped from some small interval here. In that case, we say the limit exists. Now, this is a little abstract, so let's take f of x equals square root of x as our function and prove that the limit as x tends to 0 from slightly positive values is 0. In other words, I'm not going to let x take negative values because then I'd get over here imaginary numbers. Okay, so our situation is the following, that if this is the point 0 and this is the point square root of epsilon, then x equals 0 gets mapped into this point and x equals epsilon gets mapped into this point. As I make the value of epsilon smaller and smaller, you can see that this point will get closer and closer to 0, and corresponding to that, the x point will get closer and closer to 0 as well. Therefore, our definition is fulfilled, and f of x equals square root of x has limit 0 as x tends to 0. Finally, let me take a theorem that's easy to prove using the definition that I just gave you. Suppose that the limit of f as x tends to a exists and is equal to L, and similarly for g. In that case, the limit of f plus g, that is a new function f plus g, the limit of f plus g as x tends to a is the sum of the limits, L plus m. Obviously, if I have sine of x plus 2, x squared, as x tends to 0, then from the above theorem, the limit is sine of 2 plus 2 times 4, which is 8. And that would be the limit as x tends to do. If I take the product, in that case, the limit as x tends to 2 would be sine of sine x into 2x squared. That's the product, which would be 8 times sine of 2. Here, of course, it's very similar, but it's important that L not be equal to 0. Not only must the limit exist, but it must not be a 0 limit, because otherwise one would get 1 over 0, which is undefined. So, for example, if I take the limit of 1 over sine x as x tends to a, this would be 1 over sine of a, but a cannot be 0 or pi or other such values where sine of pi would vanish or sine of 2 pi would vanish and so forth. Now that we have a good understanding of the meaning of limits, we're going to be able to discuss continuous and discontinuous functions in the next lecture.